Welcome to Homework Lib.
For this problem, the number of electrons that can be excited from the valence band to the conduction band we will denote it as n. This n should be equal to the total energy that is available to the electrons, E, divided by the amount of energy that is needed to excite a single electron, E0. So we will compute this E and E0 separately. For E, this energy is provided by the gamma ray photon. For a photon, we know the energy is h times f, where h is the Planck constant and f is the frequency of the photon. In this problem, we're not given the frequency, but we're given the wavelength. So we will need to use the relationship f equals c over lambda, where c is the speed of light and lambda is the wavelength. So plug this in, we get E equals hc over lambda. And now we use the numbers. The Planck constant is 6 times 6.4 times 10 to the negative 34 joule second. And speed of light is 3 times 10 to the 8 meter per second. And wavelengths are given in the problem, which is 9.31 times 10 to the negative 4 nanometer. However, here we need to be careful. We need to change this nanometer into the standard unit, meter. So we know 1 nanometer is 10 to the negative 9 meters. So here we simply have 9.31 times 10 to the negative 13 meters. Okay, 13. Then calculation gives us this E to be 2.14 times 10 to the negative 13 joule. Okay, now that we have computed the total energy, we will turn to the E0. So let's create another slide. E0 is the same as the gap between the valence and the conductance band, which is 1.12 electrovolts. We need to change this electrovolts into joule. We know 1 eV is equal to 1.602 times 10 to the negative 19 joule. So then plug this in. We get E0 equals 1.79 times 10 to the negative 19 joule. Now we can plug in this E0 and this E back to the first expression and get N equals 1.2 times 10 to the 6. This is the number of electrons that we're looking for.